Article 310.16b of the National Electrical Code prohibits the use of a single neutral conductor with a cross-sectional area larger than the combined cross-sectional areas of its associated circuit conductors unless the neutral is used solely for supply nonlinear loads. There are several reasons for this code restriction addressing overheating, voltage balancing, and cost. Firstly, using a larger neutral conductor than the circuit conductors can create a potential for overheating in the circuit conductors. The rationale here is that the neutral will not necessarily carry the same amount of current as the circuit conductors under normal balanced load conditions. When the neutral conductor is significantly larger, it may not dissipate heat as effectively as the smaller circuit conductors which are carrying the bulk of the current. This can lead to a build-up of heat in the circuit conductors, potentially damaging the insulation and creating a fire hazard. Secondly, using a larger neutral conductor can result in voltage imbalances in the circuit. This can lead to equipment malfunctions and reduced energy efficiency. In a balanced three-phase system, the neutral conductor ideally carries very little current, as the currents from each phase should cancel each other out. However, if the loads are not perfectly balanced, or if there are harmonic currents present, the neutral conductor will carry some current. If the neutral conductor is significantly larger than the phase conductors, it can have a lower impedance. This difference in impedance can cause voltage imbalances, where the voltage drop across each phase is not equal. These voltage imbalances can negatively impact the performance and lifespan of sensitive electronic equipment. Thirdly, using a larger neutral conductor can increase the overall cost of the installation. Larger conductors require more material and are therefore more expensive. In addition, larger conductors may require larger conduit or raceways, which also adds to the cost. Unless there is a specific reason to use a larger neutral conductor, such as to accommodate nonlinear loads, it is generally more cost-effective to use a neutral conductor that is the same size as the circuit conductors. It is important to note that the dirting factor for multiple conductors in a raceway or cable does not apply to the neutral conductor. The neutral conductor must be rated for the full load current of the circuit. This means that the neutral conductor must be able to safely carry the maximum amount of current that could flow through it under any operating condition. When determining the appropriate size for a neutral conductor, it is crucial to consider the type of loads that the circuit will be serving. For linear loads, such as incandescent lighting or resistive heating, the neutral current will typically be the same as the phase current. However, for nonlinear loads, such as electronic equipment with switching power supplies, the neutral current can be significantly higher than the phase current, due to the presence of harmonic currents. In these cases, it may be necessary to use a larger neutral conductor or to install a dedicated neutral conductor for the nonlinear loads. To reiterate, the NEC places restrictions on using a neutral conductor that is larger than the phase conductors for several reasons, including the potential for overheating of the phase conductors, voltage imbalances, and increased cost. Unless the circuit is serving nonlinear loads that require a larger neutral to handle harmonic currents, the neutral conductor should generally be sized no larger than the phase conductors. Always consult the NEC and other applicable codes and standards when designing and installing electrical systems. When dealing with multiple conductors in a raceway or cable, it's important to understand ampacity dirting. This means that the allowable current carrying capacity of each conductor is reduced when multiple conductors are bundled together. This reduction is necessary to prevent overheating, as the conductors generate heat, and the more conductors there are, the more heat is generated within the confined space of the raceway or cable. The NEC provides tables that specify the ampacity dirting factors for different numbers of conductors. These tables are based on the conductor insulation type and the ambient temperature. For example, if you have 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor may need to be reduced to 80% of its original value. This means that a conductor that is normally rated to carry 20 amps for instance, would only be allowed to carry 16 amps in this scenario. It is important to carefully consider ampacity dirting when designing electrical circuits to ensure that the conductors are adequately sized to carry the load without overheating. The neutral conductor's role in carrying unbalanced current is a key aspect of electrical system design. In a three-phase system, The neutral conductor provides a return path for current when the loads on each phase are not equal. If the loads are perfectly balanced, the currents in each phase cancel each other out, and the neutral conductor carries no current. However, in most real-world scenarios, the loads are not perfectly balanced, and the neutral conductor will carry some amount of current. The amount of current that the neutral conductor carries depends on the degree of imbalance in the loads. The more unbalanced the loads, the more current the neutral conductor will carry. In single-phase systems, the neutral conductor always carries the same amount of current as the phase conductor. This is because there is only one phase, so there is no possibility of the currents cancelling each other out. It is important to properly size the neutral conductor to ensure that it can safely carry the maximum amount of current that it is expected to carry. If the neutral conductor is too small, it can overheat and potentially cause a fire. Grounding and bonding are essential safety measures in electrical systems. Grounding provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and to energize the circuit. Bonding connects all of the metal parts of the electrical system together, such as the metal conduit, enclosures, and equipment granting conductors. This helps to ensure that all of these metal parts are at the same voltage potential, which reduces the risk of electric shock. The grounding electrode conductor connects the grounding system to the earth. This helps to stabilize the voltage of the electrical system and provide a path for lightning strikes to dissipate into the ground. Grounding and bonding are required by the NEC and other applicable codes and standards. It is important to ensure that electrical systems are properly grounded and bonded to protect people and property from electrical hazards. Consider the impact of harmonic currents produced by nonlinear loads. Nonlinear loads, such as electronic equipment with switching power supplies, can generate harmonic currents. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency 60 Hz in the United States. These harmonic currents can cause a number of problems in electrical systems, including overheating of conductors and transformers, voltage distortion, and equipment malfunctions. The neutral conductor is particularly susceptible to harmonic currents, as it can carry the sum of the odd-order harmonics from each phase. In some cases, the neutral current can be significantly higher than the phase current due to the presence of harmonic currents. It is important to consider the impact of harmonic currents when designing electrical systems, especially when serving nonlinear loads. In some cases, it may be necessary to use a larger neutral conductor or to install a harmonic filter to mitigate the effects of harmonic currents. Let's talk about voltage drop calculations. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Voltage drop can negatively impact the performance of electrical equipment. If the voltage at the equipment is too low, it may not operate properly or may be damaged. The NEC recommends that the voltage drop in branch circuits should not exceed 3% and that the voltage drop in feeders should not exceed 5%. To calculate voltage drop, you need to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of the conductor depends on its material, size, and temperature. There are various online calculators and software programs that can be used to calculate voltage drop. It is important to consider voltage drop when designing electrical circuits to ensure that the voltage at the equipment is within the acceptable range. Regarding conductor insulation types, conductors are available with various types of insulation. The insulation type affects the conductor's ampacity, temperature rating, and resistance to moisture and chemicals. Some common insulation types include THHN, THWN, THW, and XHHW. THHN insulation is commonly used for dry locations. THWN insulation is suitable for wet or dry locations. THW insulation is also suitable for wet or dry locations and has a higher temperature rating than THWN. XHHW insulation has a high temperature rating and is resistant to moisture and chemicals. The choice of insulation type depends on the specific application and the environmental conditions. It is important to select the appropriate insulation type to ensure that the conductor can operate safely and reliably. Additionally, there are different wiring methods, including conduit, cable, and open wiring. Conduit is a metal or plastic tube that is used to protect conductors. Conduit provides excellent protection against physical damage and moisture. Cable is a factory assembly of two or more conductors that are enclosed in a sheath. Cable is easier to install than conduit, but it does not provide as much protection. Open wiring is a method of installing conductors without any protection. Open wiring is only allowed in certain limited applications. The choice of wiring method depends on the specific application and the requirements of the NEC and other applicable codes and standards. Be sure to consider ambient temperature correction factors. The ampacity of a conductor is affected by the ambient temperature. The higher the ambient temperature, the lower the ampacity of the conductor. The NEC provides tables that specify the ampacity correction factors for different ambient temperatures. These tables are based on the conductor insulation type. For example, if the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor may need to be reduced. It is important to consider ambient temperature correction factors when designing electrical circuits to ensure that the conductors are adequately sized to carry the load without overheating. Let's consider the short circuit current rating, or SCCR, of electrical equipment. The SCCR is the maximum amount of short circuit current that a piece of equipment can safely withstand without being damaged. It is important to ensure that the SCCR of the equipment is high enough to withstand the available short circuit current at the point of installation. The available short circuit current depends on the utility's transformer capacity and the impedance of the electrical system. The SCCR of the equipment is typically marked on the equipment nameplate. If the available short circuit current is higher than the SCCR of the equipment may be damaged during a short circuit event. In this case, it may be necessary to install overcurrent protective devices with a higher interrupting rating or to use current limiting devices to reduce the available short circuit current. Overcurrent protection involves circuit breakers and fuses. Circuit breakers and fuses are overcurrent protective devices that are designed to protect electrical circuits from overloads and short circuits. Circuit breakers are reusable devices that trip and open the circuit when overcurrent occurs. Fuses are single-use devices that melt and open the circuit when an overcurrent occurs. The size of the circuit breaker or fuse must be properly selected to protect the circuit from overcurrents without causing nuisance tripping. The NEC provides tables that specify the maximum allowable overcurrent protection for different conductor sizes and types of equipment. It is important to properly select and install overcurrent protective devices to ensure that the electrical system is protected from overcurrent hazards. Now, let's get into the equipment grounding conductor, or EGC. The equipment grounding conductor provides a path for fault current to flow back to the source in the event of a ground fault. The EGC is typically a green or bare copper wire that is connected to the metal parts of the electrical system, such as the metal conduit, enclosures, and equipment housings. The EGC must be properly sized and installed to ensure that it can safely carry the fault current back to the source. The size of the EGC is based on the size of the overcurrent protective device protecting the circuit. The EGC must be connected to the grounding electrode system at the service entrance. Proper grounding of electrical equipment is essential for safety. Regarding the neutral conductor in a multi-wire branch circuit, a multi-wire branch circuit is a circuit that shares a neutral conductor between two or more hot conductors. Multi-wire branch circuits are commonly used to supply 120 volts fault loads from a 240 volts fault or 208 volts fault source. The neutral conductor in a multi-wire branch circuit must be sized to carry the maximum unbalanced load. The unbalanced load is the difference between the current flowing through the hot conductors. If the loads are balanced, the neutral conductor will carry very little current. However, if the loads are unbalanced, the neutral conductor will carry the unbalanced current. The NEC requires that the neutral conductor in a multi-wire branch circuit be sized at least as large as the ungrounded conductors. It is important to properly size the neutral conductor in a multi-wire branch circuit to ensure that it can safely carry the unbalanced load. Consider the use of isolated ground receptacles. Isolated ground receptacles are receptacles that have a separate grounding conductor that is isolated from the normal equipment grounding conductor. Isolated ground receptacles are typically used in sensitive electronic equipment to reduce electrical noise. The isolated grounding conductor is connected directly to the grounding electrode system at the service entrance. The use of isolated ground receptacles can help to improve the performance and reliability of sensitive electronic equipment. Now let's discuss the importance of proper torquing of connections. Proper torquing of connections is essential for ensuring that electrical connections are reliable and safe. When connections are not properly torqued, they can become loose over time, which can lead to overheating, arcing, and even fires. The NEC requires that all electrical connections be torqued to the manufacturer's specifications. Torque wrenches should be used to ensure that connections are properly torqued. It is important to periodically inspect electrical connections to ensure that they are still properly torqued. Finally, let's discuss the use of arc fault circuit interrupters, or size. A size are circuit breakers that are designed to detect arc faults. Arc faults are dangerous electrical faults that can cause fires. A size trigger the circuit breaker when an arc fault is detected, which helps to prevent fires. The NEC requires the use of a size in many areas of the home, such as bedrooms, living rooms, and dining rooms. Size are an important safety device that can help to protect people and property from electrical fires. These concepts and guidelines are important to know when sizing and installing electrical component.